Okay, so Assalamualaikum and good afternoon, everyone. So in previous lecture, we have learned about to determine determining the stability of a system using Raut-Hurwitz criteria. So Raut-Hurwitz criteria, basically you are not required to find the poles of the transfer function, but you only use table method to determine whether a transfer function is stable or not stable. So in Raut-Hurwitz criteria, you are not um, finding the roots of the denominator or finding the poles. But in this topic, in chapter 4, we are going to look at root locus. So root locus basically is a type of plot that shows the variation of the poles when you vary the value of the gain k of a system. So in previous lecture, you also have learned about finding the range of k, the range of gain k for a stable system, but you are finding k in range values only. But in this root locus topic, we are going to learn about finding the specific k value and the specific poles for stability of the system. Okay, we will go into the definition and also into more about what is root locus and how to use root locus. Okay. So in this topic, students will be able to aware about the control system problems that requires properties of root locus or require the use of root locus. And secondly, aware about complex number and how to represent complex number in vector. And lastly, define the root locus. Oh, sorry, second last. And lastly, determine the properties of a root locus. All right, so root locus. Root locus is a graphical presentation of closed loop poles as a system parameter or gain k is varied, and it is a powerful method of analysis and design stability and transient response. So usually you are given this kind of system, closed loop system, and you have forward transfer function g and feedback transfer function h, and you also have the gain k or parameter k. So in Raut-Hurwitz criteria, you have learned about finding the range of k for system stability using table method. But in root locus, you are actually finding, you are actually try to plot or try to sketch a graph that a graph of poles as you vary the value of k. So different k value will produce different poles or different poles for the closed loop system. Okay, so we will see more about this. So to understand root locus, you have to understand first the control system problems that requires root locus and how to represent complex number into vector. So let's say you are given a feedback control system as shown here. So you have forward transfer function k times gs and the feedback transfer function hs. So this is feedback system, feedback loop. So you can simplify this using feedback formula. So there are two types of transfer function. So the first one, we call it open loop transfer function. So open loop transfer function is simply k times g times h. And also you have another transfer function, we call it closed loop. So closed loop, basically you simplify this block diagram. using feedback formula. So you get Ts equals k times g divided by 1 plus k times g times h. Okay, so if you look at the denominator here, the denominator now depends on k. So if you want to find the poles for this transfer function, then you need to remember that it will depend on the value of k. So the poles depends on k. So what I'm trying to say is that, let's say you are given a system shown here. So this is the forward transfer function, k divided by s times s plus 2. And the feedback transfer function equals 1. So let's say you use a value of k, let's say 0.5, and then you try to plot the time response of the system. So you will get something like a graph shown in red. Okay, so this is under them. And then let's say you use a different k value, for example, maybe 2.0, you give k equals 2.0. What you will get is this green graph here. And if you see, this graph has some overshoot. After overshoot, it will reach the steady state value. If you compare the green and the red, both of them will reach steady state, but the behavior is different. One is under them, one is over them. And if you, let's say, take k equals 15, then the behavior of the system will be greater, meaning that it will have greater overshoot and will have some oscillation before reaching steady state value. So what this figure tries to show is that when you vary the value of k, then the system will behave differently. So we have learned in second order system that there are 4 types of nature of the response of second order system. So you have under them, over them, critically them, and also undam. And all of this nature depends on the poles of second order system. But now what you see here is that the step response or the time response of the system also depends on the gain k you give to the system. So instead of depends on poles, it also depends on the gain k. Okay, so there are 2 things that decide or determine the nature of the response of a system. You have gain k and also the poles. So the problem with control system is that we need to look at the derivation of the transfer function or the closed loop transfer function. So this is the closed loop transfer function shown here. So here it is difficult to find the poles because it depends on k. The denominator here depends on k. So the poles location will vary with the gain k here. So when you give different k value, then the poles will be different. So let's look at how this is difficult. Okay. So this is the closed loop transfer function. So each of the transfer function g and h can have its own numerator and also denominator. So you can expand, each of them has numerator and denominator. And then you further simplify this equation, you will end up with this last equation here. So the last equation here, if you take the open loop transfer function of this equation, then you will see that it has k in it. Okay, so here you have k in the denominator, and here you have k as well. So here this k actually the poles is actually depends on what k value you give. Okay, if you give k equals 0, then the poles will depend on dg and dh only. But let's say if you give k equals some big number, then the poles will depend on NG, and NH. So this example wants to show you that control system, the poles, to determine the poles, it will depend on the value of gain you give to the system. So here is what I'm trying to say. So combination of numerator and denominator of forward and feedback transformation. So poles depend on gain K. So the denominator here has gain K here. So to find the poles, you need to know the value of K for a specific system. So therefore, closed loop system, the poles are not easily obtained and changed with the value of K. So let's say you are, let's say we look at an example. So let's say you have G forward transformation equals S plus 1 divided by S times S plus 2. And feedback transformation, H equals S plus 3 divided by S plus 4. So the open loop system, you use the formula just now. So here it's easy to find poles. So poles is 0, minus 2, and minus 4. But for closed loop, then the formula will become slightly difficult because you have K on the denominator. So when to find the poles, you have to factor and you have to know that it also depends on K. So here the poles are probably 0, minus 2, minus 4, and maybe minus 1 times K, minus 3 times K. So you don't know what are the poles, okay? What are the values of poles that for this closed loop transfer function. So that's why we need a new technique or new method so that we know when we vary the value of K, what are the values of poles you will get, okay? So how this variation can be represented by some figures or some graphic, okay? So we use a technique called root locus to help find the poles. Okay, so that's the problem. Okay, so now we look at how to represent complex number in vector. So I think you have learned this back in calculus first year or back in matrix or diploma. You have learned about complex number. So you can plot complex number in Argand diagram, okay, or S-plane. So what is the complex number? So complex number consists of real part, sigma, plus J times omega. So omega is the imaginary part. So complex number can be a vector, can be represented by vector. So here, if you have an S-plane, so S-plane, the x-axis is made up of the real part of the complex number, and the y-axis is made up of the imaginary part of the complex number. So if you plot S equals sigma plus j omega, so this is the point, sigma and j omega. So here you can draw a vector line. So you can represent this by finding the magnitude of the vector and also the angle of the vector measured from the real axis. Okay, so you can represent complex number in terms of the magnitude and also the angle of the vector from the real axis. So vector also has magnitude and direction. So to find the magnitude, m basically equals square root of sigma square plus omega square. And the angle, you have to remember that it is measured from real axis. So it is always measured from here to here. So if your complex number lies on this section of the S-plane, then you can use tangent minus 1 omega divided by sigma. So for example, if your complex number is here, then the angle must be measured from real axis to the vector. So to find this angle, then you need to use or to modify this formula slightly. Okay, so by either use 180 minus tangent, or you can use 90 degree plus. Okay. Okay, ni belajar dulu masa sekolah. I cannot explain what is the logic behind, but I think you have learned before. But we will see example later. Okay, so therefore we can also represent complex number S as S equals magnitude. This symbol is angle. So magnitude, angle, theta. Okay, so instead of S equals sigma plus j omega, you can also represent this in terms of M angle omega, M angle theta. Okay, so let's look at another things about complex number. So let's say if we have a function that depends on S, and how to represent the complex number. So for example, you have Fs equals S plus A. So you can replace S with sigma plus j omega. Then you get Fs equals sigma plus A plus j omega. So this is the real part. And this is the imaginary part. So the function f will form a new complex number when you substitute s equals sigma plus j omega. So if you plot this graphically, then sigma plus a is here, j omega here. Let's look at example. Okay, so let's say you are given s equals 5 plus 2 times j, and you are given a function f equals s plus 3. So first you substitute this into fs. So you will get 8 plus j times 2. Then you can plot, for example, here the example shows a plot of this new complex number. So 8, 2j, it's here. And this line here is the complex number s. So 5 plus 2j. So when you plot for f, so f is here, same vector. So if a complex number is substituted into a complex function f, so another complex number will form. Okay, this is the things that the slide wants to show you. Okay, abaikan yang lain-lain. Okay, so in general, you can also describe f in terms of magnitude and angle. So let's say your function f is in the form of fraction. So let's say you have numerator and denominator. So the first thing to do is to find the zeros and the poles of the transfer function. So then you can find the value m by calculating the product. This is symbol product of the length of 0 divided by the product of the length of pole. So you will get the value of magnitude m of the transfer function. And then to find the angle of the transfer function, basically you need to calculate the sum of the zero angles minus the sum of the poles angle. Okay, so there are two formulas. To find m, basically you calculate the product of zero length divided by the product of the pole length. And to find the angle of the transfer function, you basically calculate the sum of the zero angles minus the sum of the pole angles. Okay, let's look at example. Okay, so let's say you are given fs equals s plus 1 divided by s times s plus 2. And you are given s equals minus 3 plus j4. Okay, so the first step you need to do is to substitute s into the transfer function. So you substitute first, then you will get something like here. Simplify, you get minus 2 plus j4 divided by minus 3 plus j4 times minus 1 plus j4. And then after that, you separately calculate the value of m and theta for each of the pole and zero of the transfer function. So first we look at this complex number. So this complex number, you calculate the m. So m equals 2 square plus 4 square square root. So you get square root 20. Okay, so it's here, square root 20. And then you determine the angle of this complex number. So to determine the angle, my suggestion is to first plot this in Argand diagram or in S-plane. So you have 4 here and maybe minus 2 here. Okay, then you sketch the line. So the angle must measured from positive x axis or positive real axis to the vector. So it's here. So this angle equals theta equals 90 plus tangent minus 1 4 over 2. Okay, and it also equals 180 minus tangent minus 1 2 over 4. So you will get this value. Okay, kita kira dulu betul tak? Oh, salah. Okay, silap kat sini. So this is 2 over 4. And this is 4 over 2. Okay. So this depends on how you look at the angle. Okay. So I think some of you know how to calculate. Some of you might confuse how do I get 90 plus or 180 minus. Okay. But this is you need to look at you need to calculate based on how you look at the angle. Okay, where you measure the angle. Okay. So when you calculate each one of them separately, okay, so this one you also calculate the m and also the theta, and this one also m and theta. Then you calculate the overall magnitude and angle. Okay, so for the overall magnitude, simply find the product of the magnitude of 0 divided by the product of the magnitude of the poles. Okay, so square root 20 divided by 5, which is the magnitude of this, times square root 17, the magnitude of this. So you get the final M. And then the angle, basically you find the sum of the zero angle minus the sum of the pole angles. Okay, so this is the angle for zero, and these two here are the angle for the poles. Okay, so this is the angle, and then you represent the transfer function in terms of m angle theta. Okay, so you'll get this one. Okay, this is how you can plot the complex number, the transfer function separately, and then calculate the angle. Okay. All right. So to test your understanding, you can try to do quiz 11, question number 1. Okay, you can try now. I give you around 10 minutes and then we continue. Okay, do you have a question for this? Okay, so we can continue with our next subtopic. Okay, so now we define the meaning of root locus. Okay, so root locus basically is a graphical presentation of closed loop poles as system parameter variable. Okay, so this is invented by W.R. Evans, 1948, and it's a method to analyze and design control system for stability and transient response. And let's look at an example how actually root locus is formed. Okay, so let's say you are given a system of camera. So this is a camera, and you want to control the position of camera angle. Okay, whether it can either go up or go down. So in the camera, you have several subsystems. So for example, you have amplifier K1, and also you have a motor and camera. And the transfer function of motor and camera is given by K2 divided by S times S plus 10. And it's a unity feedback system. So this feedback, we call it unity. So unity feedback system. And first, you need to simplify the block diagram to get into a single block diagram. So here you get K divided by S squared plus 10S plus K. So K equals K1 times K2. So from the transfer function, first what you need to do is to substitute a value of K from, let's say, 0 to a value of K that is big enough, okay, maybe reaching somewhere to infinity. So here the example given, it use K equals 50. So when you substitute K equals 0, you will get the poles equals minus 10 and 0. And you substitute K equals 5, you will get a different value of poles. Now it becomes minus 9.4, 9.47, and minus 0.53. Then you repeat the process for different value of K. And you will see that the K value will change from minus 10 and 0 to a new value. I would say a constant, a more constant value. Here you will see that the poles from minus 10 becomes minus 5 plus J5. And the second pole from 0 to minus 5 and minus J5. So you will see that K, when you varies the value of K, the poles changes from one value to another, but it will reach some constant value. Then you can try plot all of these poles into an S-plane. So for example, here K equals 0, you plot the poles at minus 10 and at 0. And repeat the process at K equals 5. So here, when K equals 5, then pole is somewhere minus 9.4 and around negative 0.5. And you repeat the process, and you will see that it shows some pattern, okay? Like a cross pattern. And then what you need to do is you connect all these points to form a graph or a lines. So what you will get is something like shown here. So it will start from here and then move to a center value here at -5, and then it goes down, okay? And same thing for this part. It will start from 0, go to -5, and then go up. Okay, so when you plot the root locus, when you connect all the lines, you will see a pattern, a graph form. So this graph is what we call root locus. Okay, the variation of the poles when you vary the value of k. So root locus basically represent the path of closed loop poles as the gain vary. Okay, as the gain vary. So this is an example of root locus. So what information you will get here is that when k is 0, the root locus start at -10 and also 0. As you increase the root locus, it will travel to a center value, an intersection at -5, and then it will go up as you increase k further. So this we can explain this in terms of the system stability. So you know already that whenever the poles are on the left-hand side of S-plane, then the system is stable. Unless you have poles on the right-hand side, then the system is unstable. Okay, but we can learn more furthermore about this root locus. For example, for k in between 0 and 25, which means from here to here, since the root locus is on the real axis, then the system is overdamped. And when k is at 25 here, then the system is critically damped. And for k bigger than 25, which is the root locus part here and also here, the system is underdamped. And overall, the system is stable for any k value bigger than 0 because there is no poles on the right-hand side of the system. So from the root locus, you can understand the system stability only by looking at where the root locus are located in the S-plane. Okay, that's the definition of the root locus. Okay, now we'll look at the properties of root locus. Okay, so the first properties of root locus, we need to look at the closed loop transfer function first. Okay, so from the closed loop transfer function, we know that this value must equals to 0 to find the poles. Okay, to find the poles meaning that you need the denominator equals 0. Rearrange, then you get k times g times h equals -1. So -1 is a complex number. So if you plot -1 in S-plane, so it's this vector. So this vector has magnitude m equals 1 and the angle is 180 degree measured from the real axis. So you can define k times g times h in terms of magnitude and angle like this. 1 angle 180 degree. So when you define the denominator k times g times h equals -1 in this form, then there are two kinds of condition. First is the magnitude condition. So the magnitude of k times g times h will be equals 1. And you can find k equals 1 over g times h magnitude. And the second condition is the angle. So the angle of k times g times h equals 2 times k plus 180 degree. So k starts from 0, 1, 2, and so on until you find until the angle becomes bigger than 360 degree. Okay, let's look at example on using these two conditions. So given a unity feedback system, forward transfer function gs equals k times s plus 2 divided by s squared plus 4s plus 13. So the question is this point minus 3 plus 0j is on the root locus? And the second point is, if the point is on the root locus, find the value of k. So the steps required to answer these two questions is, first you need to determine the zeros and poles of the forward transformation. Okay, so from the forward transformation you determine the zeros and poles. Secondly, you determine the angles from zeros and poles to the point of interest or to the interested point. The third one is then you need to calculate the length of the vector from zero and poles to the interested point. Then you add all the angles. If it is multiple of 180, then the point is on the root locus. And lastly, to determine k, you use the length of zero and pole vectors. Okay, let's look at how to determine how to answer this question. Okay. So firstly, you determine the zeros and poles of the forward transfer function. Then you plot the poles and zeros on S-plane. Also plot the point of interest. So the point of interest just now is minus 3 plus 0j. Okay, so from this transfer function, you calculate the zero and pole. So here the zero is minus 2. And the pole is minus 2 plus 3j and minus 3j. So the poles is here and the zero is in between. So usually we represent poles using X and we represent the zero using circle. Okay. And then you also plot the point of interest, which is here. Okay. So you don't use X, you use something else. And then after that, you determine the angles from zeros and poles to the point of interest. Okay, first you draw the lines that connect the poles and zeros to the point of interest. So for example, θ1, you draw a line that connects this pole to minus 3. And then after that, you determine the angle of this line from the real axis. So it measures from this axis to the line, the vector line. So to determine θ1, basically you can use 270 minus tangent minus 1, 1 over 3. Or you can use 180.
So ada orang ketuk pintu sir.
Jangan apa? Bro. tak terkejut pun. Sorry about that. Apa tu, selingan. Bongit betul. So 180 Tak okey je, tak terkejut pun. 180 plus tangent.
Takkan siang-siang pun takut se. Cik.
Tak takut pun. Ada orang lah dalam bilik ni. Oh, 180 plus tangent 3. Betul ke? Plus tangent 3. Yelah, barusan belajar kan, kena buat lawak juga. So you get the same thing, 251 plus 0.57. Okay, so it depends on how you look at the angles, okay? Pandai-pandai lah cari. Okay. And then to find theta 2, basically you draw this line, connects from this 0 to the point of interest. So basically it's a straight line. So theta 2 is 180 degree. And to find theta 3, you can use the same concept. So here it uses 90 plus tangent minus 1 over 3. Okay, after you found all the angles, you sum, okay? You sum all the angles, add all the angles, and if it's equals to multiple of 180, then the point is on root locus. Okay, tambah. Then you get minus 180 degree. So this is multiple of 180 degree. Then the point is on the root locus. Okay, then you determine, you want to determine the length, the k, okay, the value of k at the point of interest. So first determine the length of vector from zeros and poles to the point of interest. So you determine this length and this length and this length. Okay, there are 3 lengths. So you can use trigonometry, okay? Or you can use square root, okay? Square 3 squared plus 1 squared. So you get 3 values. Then to determine k, you use the formula here, okay? So to find the magnitude here, so basically you just use, sorry silap. Okay, so to find m, basically you use the concept that we have learned just now. So m equals the product of zero length divided by the product of pole length. So zero length is 1, the pole length is square root 10 and square root 10. So you get 1 over 10. Substitute balik. So k equals 10. Okay dah beda. Okay. So can you try question 2? So basically question 2 is the same, okay? Same with the example that I gave to you. But it's good if you can try this question without looking at the answer. Okay? So I give you about 5 minutes, okay? Oh, habis. Quiz 1 ni hantar nombor 1 je lah, hantar semua, okay? Jangan harap nak hantar nombor 1 je. Bila last hantar quiz waktu yang sama macam biasa hari Ahad 11.59 malam 11:59 PM Sunday quiz 11 and quiz 12. So quiz 12 I will upload the video in YouTube. Okay. And in that video also there is a take home assignment, take home quiz. So take home quiz you have to submit next week. Okay, so only this week only submit quiz 11 and quiz 12. Okay, so do you have any question for this topic? Okay, if you have any question, you can ask before I end this session.
Sir, yang ni Sir post YouTube kan Sir?
Ya, yang lecture untuk esok sebab saya tak ada esok, saya akan post dekat YouTube. So
Okay, sir.
jangan lupa subscribe and
Okay, sir.
give thumbs up.
Leceh rasa macam belajar dekat online. Lain teruk lah. Hai, saya lagi suka face to face.
Kan gitu. Bila face to face tak datang kelas gitu, tak adalah main je.
Saya datang je. Saya tak pernah ponteng kelas saya. Online ni start-start je. Lain tak cantik lah.
Lain UMP pun tak cantik.
Oh, saya kat UMP eh?
Ya, semalam tengah kelas tiba terkeluar sendiri. Saya yang terkeluar.
Tak apa sebab ilmu dekat Sir ni kita orang tak ada ilmu nak menuntut ilmu lain slow.
Itulah kesian kan. Tak apalah ada YouTube. Tapi YouTube video tu korang boleh lajukan lah. Pandai-pandai lah lajukan ataupun skip mana yang saya bebel ke. Rasa pandai-pandai lah skip sebab dia panjang
Okay sir.
Okay, so we will continue more about root locus next week. So in tomorrow's lecture, which is a video that I will upload in Kalam, there's a section, the end section, where I couldn't calculate the answer. Okay, so I made a mistake and I stopped the class somewhere after halfway after the calculation. Okay. And we will go into discussing your quiz 12 next week. So quiz 12, basically you have to sketch the root locus. Okay, sketch the root locus using properties, a lot of properties that you will learn later in YouTube video. And we will also go more about understanding root locus using different question and example. Okay. So root locus is a famous question in final exam. Usually one question, 25 marks over 100, around 10%, around 10 over 40%. And usually root locus is very difficult. Okay, most students when they calculate halfway, they couldn't get the answer, and then they just blank. Okay, blank or just leave the question unanswered. So what I want you to do is to practice. Okay, practice calculate or try to calculate the answer so that later during the exam you at least can get maybe 10 marks out of 25. At least you can get something. Okay, don't leave the question unanswered. Okay, so that's all for today's lecture. So see you guys next week, inshallah. And that's it. Assalamualaikum and bye-bye.
Thank you sir.
Alright.
Sir.
Yeah, siapa?
Cuba bagi balik pesanan yang Sir bagi dekat WhatsApp tu.
Pesanan apa?
Pesanan untuk budak universiti.
Oh. Awak dapat 3 pointer kan?
Sem ni macam payah Sir.
Lagi berapa sem nak habis?
Lagi 2 sem.
Tak apa, kita tengok. Kita tengok boleh habis 3 pointer tak?
Dah Sam ni tak boleh sir sebab banyak masalah software susah. Laptop semua tinggal kat situ. Dekat UMP.
Tak apa, dengar cerita final akan buat kat UMP. So
Oh itu memang cantik lah. Final
mungkin
bila sir?
final untuk budak final year macam biasa kot, hujung sem. Untuk korang tak tahu lagi.
Oh,
So
dalam bulan berapa
separate final
sir?
year. Maybe korang punya sebelum start sem kot.
Oh ya
Maybe
ke?
bulan 10 nanti, contohnya start sem boleh masuk universiti. Dia
Ha?
akan buat final 3 minggu awal macam tu sebelum start sem.
Oh, okay.
Maybe 3 minggu awal atau 2 minggu awal korang balik, maybe revise sikit. Tak tahu lah, maybe ada revise sikit kot. Then korang terus jawab final. So kemungkinan besar final korang berderet lah. Hari ni AC, esok vibration, esok thermo macam tu, macam berapa rapat. Memang fail lah. Tak
Aduh,
sabar.
ai kau jangan macam tu sir. Aduh. Terus doakan fail lah sir.
Tak, memang hancur lah. Memang dapat rasa lah akan
Dapat rasa.
fail. Tak, memang akan. Memang akan jadi nanti. Memang banyak problem.
Tu lah.
Tapi
Harap Karimah okey lah. Kalau Karimah okey, alhamdulillah.
nanti saya cari nama awak, saya tolak Karimah.
Thank you sir.
Alright, so that's it. Bolehlah, bye-bye. Bolehlah pergi makan.
Okay sir.
Okay, Assalamualaikum. Bye.